I'm just starting the video, the YouTube live. So now we're live on YouTube. We should be. Let's check. Okay. Okay, so we have 25 participants in the room. Okay to start? I've already texted Nat, and he'll probably join in a few. Sige. Good morning, everyone. Hindi ko kayo maisa-isa, medyo madami tayo. But welcome. This is parallel session 2.2 entitled Electronics, Electrical Engineering, and Instrumentation, which officially should start at 8:30 or 8 o'clock. I'm not sure, there were some few changes that went around. Kung 8 o'clock ba o 8:30 magsisimula. But here we are. They can start at any time. And welcome to the PAASE, or the Philippine American Academy of Science and Engineering 40th PAASE anniversary, and also the 2020 annual PAASE meeting and symposium, or APAMS. Okay, we have 3 speakers for this parallel session. We have Dr. Rafael Haculbia, Dr. Nathaniel Hermosa, and Dr. Marianette Morales Vega. The first speaker is Dr. Rafael Haculbia. Let me please give a short introduction. Dr. Rafael Haculbia is a special postdoctoral researcher at the Surface and Interface Science Laboratory in RIKEN, located in Wako, Saitama, Japan. Raf obtained his PhD in physics degree at the National Institute of Physics. From 2011 to 2014, he was an instructor here at NIP and taught introductory and advanced courses in physics. In 2014, he became an intern under Professor Satoshi Kawata through the RIKEN's program for junior scientists. And he was also the Edgardo Gomez Awardee for Outstanding PhD Graduate way back in 2016. His fields of interest are nano-optics, plasmonics, of course, terahertz spectroscopy, instrument development, scanning, tunneling microscopy, and atomic force microscopy. And his talk will be on a recent work that his group did on single molecular resonance Raman effect in plasmonic nanocavity, which was published in Nature Nanotechnology just this year. So this is a very new work. So without further ado, let me welcome Dr. Rafael Haculbia to talk about tip-enhanced Raman spectroscopy and imaging of a single molecule in ultra-high vacuum and low-temperature environments. We have muted the participants of this meeting, but if you have clarificatory questions, if you may unmute yourself, and so as not to disturb the thought of the speaker, may we request the audience to please restrict your questions to short clarificatory questions, and more and questions that would require drawn-out discussions. Let us reserve them after the talk is done. So without further ado, let me welcome Raf. You may start anytime, Raf.
So again, I'm Raf from RIKEN. So I'm very happy to be invited, although I didn't initially know that the talk should be this long, but I will not talk for 45 minutes because I cannot. So again, I'm from RIKEN, and I'll discuss our recent work on tip-enhanced Raman spectroscopy in UHV, ultra-high vacuum, and low-temperature environments. So probably, as I said, I cannot talk so long about these results. So I thought I should introduce RIKEN. So RIKEN is short for Rikagako Kenkyusho. So for us, it's totally meaningless, but for Japanese, it's obvious. The meaning is obvious. So in Japanese, this is the characters. So you can read this Rikagako Kenkyusho. Then basically, it's Butsuri or physics, then Kagaku or chemistry, and this is institute. or research place, actually, literally. So officially, it's Institute of Physical and Chemical Research. So our it's not a university; it's a research institute. Institute of Physical and Chemical Research. That's why actually uh, one research scientist in our group once said that why are there many bio research in RIKEN? Because RIKEN is supposed to be Physics and Chemistry Institute. Why there are so many bio? Anyway, so RIKEN, of course, anywhere in Japan is beautiful. In April, here is a photo of our just a pond in RIKEN. And as I said, RIKEN is not a university, but a research institute. So the division is a little special, a little different. So RIKEN is separated into mainly, they said, three main clusters. So RIKEN's cluster for pioneering research, where we belong. Basically, this is anything. So the research topic is anything and only based on the direction of the PI or the principal investigator. Then there are still traditional research centers like they call it the strategic research centers, which are basically mission-oriented centers. Like its mission is on advancement of photonics or materials, mathematics, brain science, sustainability, just traditional research topics. But also there's a so-called research infrastructure. This is the user a shared large-scale equipment, basically. So like supercomputers or free electron lasers and other things. So that's RIKEN. And as I said, as I continuously say, RIKEN is not a university, but actually RIKEN has a so-called program for junior scientists, where RIKEN can accommodate students. There is so-called International Program Associate, where here foreign students are allowed, foreign students can be supported by the program who are enrolled in either Japanese university or a foreign university. Actually, UP, NIP has a memorandum of agreement for the International Program Associate. So RIKEN can accommodate students from NIP. And then they can do the research in RIKEN and obtain the degree from UP. Also, it's possible to be a junior research associate. This one is only for Japanese or foreign students enrolled in Japanese universities. So if the student is in a Japanese university, then he or she can be a JRA and still work in RIKEN, but the degree is given by the Japanese university. Also, so these are for students. I belong to a special program called Special Postdoctoral Researcher Program. So this program is basically a postdoc program for Japanese and foreign research fellows. Actually, there's more programs in program for junior scientists for PI, for example, young PI. So, but I thought it's not so interesting for or related for other people. So I just want to advertise, if interested, you should ask your advisor if you can do research in RIKEN. So as I said before, I am from Surface and Interface Science Laboratory. Our laboratory is headed by Dr. Yusuk Kim. Right now we have about more than 20 members. So one is Dr. Kim, and then 5 scientists, several postdocs and students, and some only 2 technical staffs and 1 secretary. And as a trivia, at one point we had 4 Pinoys: Celine Catalan, Katz, then Mimi. She is the first IPAC of NIP RIKEN. Then Vani also belonged to SISL once, but now she is in a different group in RIKEN, and myself. And as I always say, there is one feeling Pinoy in our group. He is watching now, my boss, basically, Dr. Hayazawa. So our group, as our group's main tool is actually the scanning tunneling microscope, STM. And the STM we use is in ultra high vacuum and low temperature. And the mission of our group, I got this from our website, is the study of energy transport and conversion at solid surfaces and interface in the nanoscale regime. So the STM is a very powerful tool for studying metal or substrate molecule interactions with spatial resolution up to the angstrom scale. So some topics our group are doing now are this. So plasmon-induced reactions in the single molecule scale, or on-surface synthesis of new materials. So making the new molecular assemblies in the surface. And yeah, I am involved in development of new tools for nanospectroscopy, because basically the STM is very good for topographic measurements. So you can see the molecule, individual atoms, in fact, but you cannot identify them. So it is basically blind. But it's strange because you can see nano objects, but basically it doesn't know what those objects are unless you support it with some form of spectroscopy or some form of calculation. Traditionally, just some form of calculation, but very recently, STM groups have been trying to develop tools together with the STM for spectroscopic experiments, optical spectroscopy especially. So if you're interested, you can check our website and some recent publications here. So as I said, I am part of the group developing new tools for nanospectroscopy. Especially, I am assigned to work on tip-enhanced Raman spectroscopies. So I thought just a brief review of Raman spectroscopy. So for example, if we have a molecule, simply diatomic molecule, then this molecule has some electronic states and vibrational states. This is not drawn to scale at all. So if we shine light to this molecule, then this molecule can be excited to a so-called virtual state. And eventually it relaxes. And this radiation is scattered. If it is scattered, then we call this radiation Rayleigh scattering. Then in the case of Rayleigh scattering, the energy of the incident light and the scattered radiation is the same. And majority of the scattered light is Rayleigh scattered, so no change in energy. But one in, I don't know, 10 million or something. So very few of the scattered radiation can be scattered inelastically. That is, the molecule is excited to the virtual state and it doesn't relax to the original state, but is instead relaxed to a little higher vibrational state. In this case, this phenomena is called the Stokes-Raman scattering, wherein the energy of the scattered radiation is different from the energy of the incident radiation. Also, the molecule the molecule can be in an excited, not excited, but a different vibrational state than the lowest electronic state. Then it relaxes to a lowest energy state. Then this is so-called anti-Stokes-Raman scattering. Basically, both are Raman scattering, just the energy of the spectrum is different. Then also, it's possible to have excitation enough to excite the molecule to a real electronic state, not a virtual state. And then in this case, so the molecule is excited to a real electronic state. Then when it comes back to not its original state, then this is so-called resonance Raman scattering. So basically, the excitation is, as I said, enough to reach the actual electronic state. So Raman spectroscopy is very strong to identify the target molecules because the vibrational states are unique to a particular mode, a vibrational mode, and by studying the combination of these modes, you can identify the molecule. So as a short example, for example, we have this fairly simple molecules, and structurally they are the same. So this is a phthalocyanine molecule. It's used as a dye. So these two molecules. So this is a phthalocyanine molecule with nothing at the center, and this is a phthalocyanine molecule with a metal on the center. This metal can be several things. For example, iron, zinc, copper, magnesium. Now, if you see this, they basically look the same to us, especially to physicists. But when you want to see what molecule this is, basically you can do Raman. Just put this molecule on the sample plate, then shine light and detect the Raman signal. And in fact, you will see that these molecules have very different Raman spectrum. So of course, since each of these Raman modes represent a vibration, a particular vibration, there can be common Raman modes between these two molecules because they are structurally the same. But as you can see here, the intensities are different and there are slight shifts of the Raman signals. And with this information, you can identify each of them. So based on the spectrum alone. So as I said, the identification of similarly structured molecules is no problem for Raman spectroscopy. And we always say that Raman spectroscopy have a good chemical sensitivity, so it can identify different structures. However, Raman spectroscopy, as I described previously, is very rare, very weak. So in fact, here is a Raman and fluorescence spectrum from zinc phthalocyanine. So you can see a very large fluorescence background and just super small, very weak Raman signals, both in the anti-Stokes region and the Stokes region. So Raman is very weak. So in fact, it's about 10 to the 14 times weaker than fluorescence and about 10 to the 10 times weaker than IR absorption. So it's difficult. It was very difficult to measure Raman, but of course, recently the detection mechanisms, better cameras, better filters allow us to detect Raman very easily. But in general, it's very weak. Moreover, the Raman being an optical technique, it's limited by the so-called diffraction limit, wherein the minimum distance you can detect between two signals, 2 points in the spatial, is about half the wavelength. So this means that if you use, say, visible light, the maximum spatial resolution you can get is in the hundreds of nanometers. And it's being the nanoscale materials in the 1 nanometer range is difficult to study with Raman, with the conventional Raman spectroscopy. That's why there are several techniques that are used in order to attain nanoscale resolution and also to enhance the Raman signal, to make the Raman signal stronger. So one of those, of course, there are several, as I said, but one of those techniques is tip-enhanced Raman spectroscopy. It was first introduced in a conference in 1999 and published in 2000 by these three, and there's one more. And tip-enhanced Raman spectroscopy is done, but basically you shine the light and detect the Raman signal, but you add a tip of a scanning probe microscope, for example, the scanning tunneling microscope or the AFM. So by putting the tip close to the molecule, you will get a very strong signal. For example, here, they found that when the tip is totally retracted, so when the tip is far, they could not detect the Raman signals. But when they approach the tip near the surface, near the molecule, they could easily get several Raman signals. And this enhancement, so the signal becomes actually infinite enhancement, but the amount of enhancement is debated how much. But basically, the source of enhancement is important. So why does this signal become stronger? So at present, there are two well-established reasons for the enhancement. And these two reasons are, one is the so-called electromagnetic enhancement. So basically, when you have it's like a nano antenna. So basically, the incident and scattered radiation are enhanced because they are isolated in this very small region, but also because of the plasmons present at the tip sample junction. So this is the so-called electromagnetic enhancement, but there is also one more so-called chemical enhancement, more popularly known as charge transfer resonance, wherein instead of the direct excitation from the molecule's lowest, highest orbital and lowest unoccupied orbital, you can, by placing the molecule near a metal, as what is always done in TERS or SIRS, you can get another source of electrons, charge transfer resonance in this case. So TERS is, Raman signal is enhanced in TERS because of these two effects, and these two effects happen simultaneously. You cannot do TERS without both of them, at least previously. So, but in fact, in TERS, it's mainly based on form of resonance. So here is some, the equations of Raman spectroscopy is very complicated, but this here is the intensity of Raman signal, and here is, so in the intensity, there are several terms, but I'd like to focus on this term, because this term you can for now ignore. So this term is the so-called Raman tensor, or the Raman polarizability tensor. So the important point is that this term is the vibrational, the energy of the vibrational mode, and this term, is the energy of the incident light. So basically, from this equation, it's easy to see that when the energy of the incident light is equal to the energy of the excited light, energy of the incident light is equal to the energy of the vibrational mode, then this term is maximum and the Raman signal is very large. So in such a case, this is the so-called resonance Raman effect. And actually, the TERS is mainly resonance with the excitation. So of course, there is so-called the ground state chemical enhancement, wherein just by placing the molecule in the environment, in the in the metal environment, the Raman signal is slightly increased. But mainly, if you choose the proper wavelength of light, you can have a resonance enhancement by the intrinsic molecular states. So you excite the molecule from its HOMO to LUMO. Then you have resonance, the molecular resonance Raman. And as I said before, charge transfer resonance is when your energy is equal to energy of the incident light is equal to this energy. So you have the so-called charge transfer resonance. And this tree is the so-called chemical effect. And the other one is the plasmon resonance effect, where your molecule, your metal has a certain plasmon resonance, and the excitation is in resonance with that plasmon energy, and then you can get another enhanced signal, basically from these equations. So in general, TERS, or the enhancement in TERS, is defined by basically the resonance, or the how far your mode is from the energy of your laser or your excited light. So TERS has been used extensively since 2000, and some examples of materials studied by TERS is this one. So this is only for scanning tunneling microscope based TERS. So here is a example of TERS mapping. So these are carbon nanotubes, and the authors found that the carbon nanotubes has strong defect signals at the end of the carbon nanotubes, and the spatial resolution they were able to reach is about 1.7 nanometers, even in ambient conditions, so room temperature and atmospheric pressures. But also so this was reported in 2014, but in 2013, the first ultra-high vacuum low temperature, but only in liquid nitrogen temperature was reported. Here, they investigated single molecules. So for a long time, it was theoretically predicted that because Raman is very chemically sensitive, and with the with the scanning probe microscope, the spatial resolution approaches nanometer or even angstrom scale. It was initially theoretically predicted that you should be able to identify, or if you take the Raman map of a molecule, then individual Raman modes should be different. So it should have different appearance. Because, for example, one Raman mode only vibrates the outer benzene rings, or one Raman mode only vibrates the inner benzene rings, but the signal, therefore, should only come from the inner part of the molecule or just the outer part of the molecule. Then it was expected that you can differentiate the vibrational mode from the Raman map. But in 2013, although this is the first report of that, they tried single molecule, really single molecule, just one molecule in a 3x3 nanometer area. They could detect the Raman signal, but unfortunately, they couldn't resolve the different vibrational modes. So it was a good result, but it's not complete. And several years after, the next one was in 2019. And in this situation, they were able to show that individual vibrational modes have different Raman maps. So in this figure, this paper was published in 2019 in Nature. So again, this is in UHV, but this time temperature is lower, 6 Kelvin. And then they found, so top one is the Raman maps. So they moved the tip across the sample and across the substrate. And then they found that individual modes show very different Raman maps. So this mode only at the center. This mode shows a cross. So here is the molecule they studied, cobalt tetraphenylfluoripyrin, I think. And they show different forms or they show that the Raman signal is strong only in distinct areas of the sample. So this result was very groundbreaking last year. And it finally experimentally verified the theoretical predictions for very long, that was predicted very long time ago. But however, in this work, in order to achieve this great result, so in fact, they have about 2 angstrom of spatial resolution. So it's, as you can see, you can separate or individually identify from one small molecule. Note that this molecule is about 2 nanometer, I think. So it's very small. And then, so you can detect the signal, difference in signal within the angstrom scale. However, in order to achieve this, they had to approach the tip. So as I mentioned before, you have to put the tip. And in this work, in order to achieve that great spatial resolution, they had to approach the tip to the molecule. And in fact, they themselves said within subatomic separation. So the distance between the molecule and the tip is very near. And although this have shown good spatial resolution and very strong Raman signal, in fact, the Raman peaks are affected. So that is, here is a gap distance dependence. So this is the separation between the tip and the molecule. And red dots are the Raman signals. So as you can see, when the tip is far, for example, this mode has 3025 wave numbers. And then as they approach to 2 angstroms, so this data were taken at 2 angstroms separation, the 3025 mode actually became a 3003 mode. So this means that with this technique, although you can get a very good spatial resolution and very strong signal, it's difficult to assess the original properties of the molecule because the measurement itself changes the molecule. And this is, they admit this problem. Well, they didn't point this out as a problem, but they admit that basically the molecule become a hybrid system of the molecule and the tip. But if we want to assess the molecule itself, so then this technique is, we cannot use this technique. So in order to solve this problem, so the conventional technique was just to place the molecule directly on the metal and then approach the STM, the metal's tip. In our case, what we did is we placed an insulator, sodium chloride, in between the metal and the molecule. So in this situation, the metal, the molecule doesn't interact with the metal, and we carefully did not approach the tip very near the molecule. Moreover, our technique could allow a variety of measurements to be done on the same sample while also keeping the original electronic structure. So when you put the molecule near the metal, the molecule's electronic states hybridize with the metal, and therefore you cannot get the original electronic structure. But as I will show earlier, with this technique, the original electronic structure is preserved, so we can study the original properties of the molecule. So as I said, our technique is based on the STM. So we use the low temperature ultra high vacuum STM, and this STM is a little special. So we have lenses inside the UHV, inside the ultra high vacuum chamber, and this is for detecting light and introducing light into the STM tip junction. So here is a schematic of the setup. So we use a continuous wave tunable laser, and then basically just detect Raman. So in fact, there's nothing so special about this setup. So we deliver the Raman signal to the STM via optical fiber, and then just detect it using conventional techniques. So we illuminate on one side and then detect on one side, and then approach the tip to that spot. And for our experiments, we use the copper naphthalocyanine molecule. And in this case, we place the copper naphthalocyanine molecule on a sodium chloride surface, as I said. So just deposit the molecule on the sodium chloride supported by silver surface. Then here is a STM image of that molecule. So here's a large scale scan showing several. So scale is about 100 nanometer. And these dots are the copper naphthalocyanine molecule. And as you can see, they are present on the sodium chloride. These are sodium chloride, and also present on the silver. And I'm interested in studying the molecule on the sodium chloride. And when I check the single molecules on the sodium chloride, so these are individual sodium and chlorine, individual chlorine atoms. So we found three different, so we found that the molecule can adsorb on the surface, so it can be present on the surface in three different configurations. So it can be parallel, this axis parallel to the chlorine, or perpendicular to the chlorine, or at some angle. But I found that of this species, this one I call the 45-degree molecule is the most abundant. So in this presentation, in our work, we just focus on this molecule. So then we measured the Raman signal, the thirst signal of our molecule. So we put the tip near the molecule, and when the tip is at the center, here, there is no signal. But as we approach the tip off center, then we can detect the Raman signal. And moreover, away from the molecule, we cannot detect any signal. So basically, this suggests that we successfully got the tip-enhanced Raman signal. Also, surprisingly, actually, we wanted to compare this signal because this is our technique basically, and this is the usual way to measure thirst. So when we place the molecule on the, when we place the tip on the metal, on the molecule on metal, we couldn't find any Raman signal. So it's quite surprising considering that this is what was previously done. So in order to investigate this point, we check the electronic states of the molecule. So scanning tunneling spectroscopy allows us to measure the electronic states of the molecule by measuring the current or the change in current as we change the bias voltage between the tip and the sample, between the tip and the substrate. So in the STS signal, so here are two scanning tunneling spectroscopy spectrum. And when the molecule is on silver, we were only able to find one peak. And whereas when the molecule is on copper naphthalocyanine, we found two peaks, one on the positive side and one on the negative side. And based on STS calculation, based on calculations, this can be identified as this one is the LUMO, or the lowest unoccupied molecular orbital, and this is the HOMO of the molecule. So in this case, also we found that when the molecule is on the NaCl, when we change the bias voltage to around 1.85 volts, we can see this kind of structure, which when we compare to the calculated molecular orbitals, they look exactly the same, basically, suggesting that also the LUMO looks the same as the molecular orbital, whereas if we change the bias voltage for the molecule on the metal, the molecule doesn't, the molecule's image doesn't change. This means that the molecule is hybridized, or the molecule's electronic state is hybridized with the metal's metal. Whereas for the molecule on the NaCl, the molecule is electronically decoupled from the not NaCl, from the sodium, from the metal surface. So the DFT calculations confirm that the molecule is in its original electronic state, which is very important in our experiments. Whereas the molecule on the metal, it's hybridized with the metal.
Rough.
Then what does this imply? So as I said before, there are several sources of enhancement in TERS. So first is the electromagnetic enhancement. So however, as I said, the molecule on the metals show no Raman signal. But in this experiment, we just moved the tip from the molecule on the sodium chloride to the molecule on the metal. And basically, there is signal here and there is no signal here. So if this means that this observation cannot be explained just by the electromagnetic effect, because the same tip is used and the same energy of the laser is used. So this electromagnetic enhancement cannot answer why there is signal here and no signal here. Also, chemical enhancement cannot be the reason, because as I said, there is no hybridization. So it means there is no channel. There is no charge transfer channel between the metal to the molecule on NaCl. So the chemical enhancement is absent, or if not really absent, it's very much reduced. So to explain our results, one more possible reason is just the direct molecular resonance. That is, instead of charge transfer, instead of tip to molecule directly, then there is just, we excite the molecule by choosing the proper excitation light. But in order to confirm this, we have to determine the absorption spectrum of the molecule. So I'm sure many of you are familiar, but it's quite easy to measure the absorption of a molecule if it's on the solution or in solid form, but it's very difficult to measure the absorption of one molecule. So, but our group was able to introduce a technique wherein, so in the absorption measurement, the conventional absorption measurement, you shine the white light to the molecule and then measure the absorbed signal. In our group introduced this technique, so-called scanning tunneling absorption, wherein the plasmon resonance, also the localized plasmon at the tip substrate junction, also it has a broad spectrum. So basically, Imada-san, one of our group members, used this light as the light source for absorption measurements. And then he found that when the molecule, when the tip is near the molecule, there was some dips in the absorption spectrum, in the scanning tunneling luminescence spectrum, and no dips in the when the tip is far. This suggests that when you divide these two signals, he was able to get this. And through calculations, they found that these two features correspond to the absorption of the molecule. So it's one of the first demonstrations of single molecule absorption. And we applied this in order to confirm our results. And we found that, yeah, for the molecule and the metal, there were no signals in the vicinity of the excitation light we used. And then when we placed the molecule on the sodium chloride, we could easily detect this dip, which corresponds to the absorption of the molecule, as also confirmed by room temperature UV vis measurements in solution form of this molecule. So we know the absorption spectrum of the molecule. We can perform resonance Raman spectroscopy. So what I did is I varied the laser wavelength excitation laser around the absorption of the molecule. And by doing this, as I showed before, that the Raman signal is very sensitive to the incident light energy, I found that the energy, the Raman signal changes a lot, and that when the energy is lower than the absorption of the molecule, then almost no signal. And then, so when we plot one or some peaks here, we can observe that the intensity varies exactly as the absorption of the molecule. This simply means that when the molecule is excited at its absorption, well, it shows maximum or very strong Raman signal, as is expected for resonance Raman spectroscopy. So actually, this is direct evidence of resonance Raman effect at really a single molecule, because in this experiment, we can only see one molecule. So aside from this evidence of resonance Raman, we also tried to perform Raman mapping. So we measured the Raman signal at several points of the molecule. So here, we can see that when the tip is placed here at the between two lobes, then this is the Raman signal. And when the tip is placed at this, we can observe this Raman signal. So very clearly, these Raman signals are a little different. So in fact, when we do the Raman mapping for this mode, we found this signal. So Raman signal is like this. And then this mode, Raman signal is like this. And in this mode, the Raman signal is like this. So we could identify 3 different Raman maps, 3 different patterns of the thirst maps for all of these vibrational modes. So in order to see why or how this happens, for example, this mode, 1389 modes, by comparing with the DFT calculations, we found that this mode, the 1389 mode, has these vibrations. And our explanation is that when you place, so this mode has a symmetry of B1G. And when we place the molecule along this symmetry axis, so for example, here, when the tip is here, these 2 modes are vibrating in phase. But when the tip is placed here, modes here and modes here are vibrating out of phase. So we propose that when the modes are here, when the tip is here, this modes is enhanced. And when the tip is here, these modes are canceled. That's why shape is like this. So enhanced signal here, and reduced signal here, and at the center. It's the same for this mode. For example, this mode, the symmetry, so the mode is like this, and the symmetry axis is like this. And then again, when the tip is here, these modes are out of sync, out of phase. And when the tip is here, the tip is in phase. Vibrations here are in phase. Therefore, this should result in such a Raman pattern. And lastly, this mode showing circular pattern, we found that this mode is so-called A1G mode, and this is basically totally symmetric mode. So wherever you place the tip, there is a maximum Raman signal, or there is a strong Raman signal, suggesting that that's why the pattern is like this. So therefore, we propose that the Raman maps we observe is defined by the symmetry. So there are 3 different symmetries of this molecule we found, and the Raman maps show that it's sensitive to the vibrational symmetry. So finally, in summary, in our work, we were able to demonstrate resonance Raman scattering, resonance Raman spectroscopy at the single molecule scale. And next, we were able to confirm that the Raman maps reveal the vibrational symmetry of the molecule. So I'd like to thank my lab mates, my co-authors, especially Dr. Kim, Dr. Imada, Dr. Hezawa, Dr. Yang, and Dr. Kazuma. And our results are supported by the theoretical work of Dr. Miwa, former member but now in Northwestern University, and the group of Taketsugu Sensei in Hokkaido University. Also, I need to acknowledge these funding agencies. So as RIKEN's program for junior scientists, and Kakenhi for my grant in aid for early career scientists grant. So yeah, that's all. Thank you.
Thank you very much, Raf, for that nice talk. Questions? Sabi na nga ba kulang yung 2.5 hours pag anim ng speakers? Wala ka pang masyadong sinabi niyan, ha?
Oo nga, sir.
Alright. Okay lang yan. Okay lang yan. That's why we have this limited number of speakers for things such as this. Questions from the audience?
Ako na muna to start the ball rolling.
Sige.
Si Mo.
Go ahead, Mo.
Hi, ma'am.
Hi, Raf. Yung single molecule, I'm just curious kung paano mo siya nata-target yung position in your slides. If you focus on, or if you put the tip at that particular position, so paano yan nakikita? From what I understand, di ba yung image, makikita mo post-processing na? Or may image ka na as you measure the absorption or Raman?
So, sandali lang po. So actually, yung pong aming Raman signals, so this is STM image po ng molecule. So it's the topographic image of the molecule. And then actually, this is taken simultaneously with this Raman map. So at the same time, we can measure the topography and the Raman signal.
So this is a single shot? So
basically single
not
shot.
Not raster scanned?
Sorry. Hindi po siya single shot. Instead, so yung tip po namin is minumove namin across like this. So raster scanned, as you said. And then we measure the spectrum at every point.
I see. Okay.
And then post-processing, yes, you're right.
And then locate that particular position.
Yes po. Then you can...
For the corresponding Raman. Okay.
Yes po.
Okay,
But,
got it.
Of course, for the other spectrum like this po, just by... we can very precisely place the tip here, actually. Sorry. We can very precisely place the tip at a certain point in the STM box. So especially the UHV low temperature STM is very, very stable. So there is almost no drift. So the molecule stays in this spot for example, in that spot of the substrate for a very long time, and you can place the tip at a selected point, and then it is at that point, basically, mainly
Okay.
because of the node drift.
Thank you. Thank you.
Raf,
Yes, sir.
you mentioned something about, thanks, Mo. You mentioned something about plasmon effect.
Yes, po.
So does it have any bearing whatsoever with how the optical properties of the material that you use for the tip should be in relation to the substrate or the sample that you are trying to image?
Yes,
Should there
yes,
be
sir.
an effect?
Yes, sir. So basically, this molecule was chosen. Sorry. So maybe I didn't describe it completely. So in our experiments, po, the substrate, the tip we use is gold, and then the substrate is silver. Well, the substrate really, if we would have wanted to use gold, but we found that it's very difficult to prepare the sodium chloride on gold, so we didn't use gold. But anyway, as you said, the plasmonic properties of the gold is very good in the 700, 600 to around 800 maybe nanometer range. And the absorption of this molecule is known to be in that range. So that's why gold tip plus the 700 to 800 nanometer laser plus this molecule is the good recipe, as you would say. So yes, it depends on the choice of the molecule, the tip, and the incident light is mainly because of the plasmon, or
All
one
right.
of the most important choices you have to make.
Okay. Thank you very much for clarifying that. I think we have a um, question from the chat. I think Ma'am Julia Salor, you can actually unmute yourself, but if not, this is the question, Ra, for you. Well, what is the significance of the study and how Raman spectroscopy can contribute to future studies? I would assume in terms of molecular science and imaging.
Yes, so so Raman spectroscopy po is widely used for identifying, say, medical molecules, possibly for use in medicine, or say for use in electronics. And basically, the interaction of a molecule on a solid surface is an important uh, point, an important topic in the field of semiconductor, for example. So how does a molecule adhere to the surface, or how does the uh, so for example, in a battery, there is the solid surface, the electrode, and then there is the liquid, or you can have a solid state battery, but basically there is an interface. So there is a uh, adhesion between the molecule and the surface, and this adhesion is the properties of this adhesion is very important because it will allow us to improve this interaction, and therefore we may be able to find new ways to use such a molecule metal or molecule insulator combination. However, if we want to so no, not however, but for the case of tip enhanced Raman, so the tip enhanced Raman can be powerful in studying these interactions because it can identify the presence of the molecule, and also it can identify if the molecule have changed its properties by attaching to the surface. So this point is quite important for nanoscale materials. And also, for example, if organic chemists are trying to make a new material, make a new chemical compound, most of the time they are not so sure about, of course they know, they have a guess of what could happen, but they cannot be so sure of the result. But using our technique, they can at least identify if the molecule is symmetric, and symmetry is also a very important aspect in such kinds of research. So these kinds of things makes this work important, I think. Thank you. Anything else?
What's so interesting about sodium chloride on silver?
Sodium chloride on silver. Actually, ma'am, I would say that the sodium chloride on silver surface is a nice template for studying insulator metal molecule interface. So because the sodium chloride is easy to make in the lab, basically, very easy. So that's one point. Of course, the sodium chloride on metal is also a topic of interest for theoretical chemists, because they, for example, in this image, in this image, we can see there are dark bands and bright bands. So this surface, silver, is a silver 111. So the topmost surface has a 111 crystal facet. Then the sodium chloride is actually 100. So in fact, there is some, there is a small mismatch, lattice mismatch between these surfaces. So then that's why this dark, light and dark bands are appearing. So the sodium chloride on silver can be used as a template for studying such small interaction, small defect. It's actually not defect, but a small mismatch of the lattice. So basically, it's a template for studying these kinds of things, I think.
Okay, thank you.
Thank you, po.
Chase, last question.
Sige. Kuya Raf,
Yes?
would the result be the same if, would your conclusion be the same if, di ba yung tinignan mo is yung 45-degree na molecule lang with respect to the silver?
Yes.
Would the conclusions be the same if you use yung 0 degrees or yung 25? I'm sure nakaano yun.
Yeah, so I think in general the conclusions are the same, but they can be a little different. Of course, I only looked at this and I only reported on this, but in fact, I have the results of this one, and I'm not ready to describe them.
Magkaiba yung selection rules eh.
Sir?
Magkaiba yung selection rules.
Yes, magbabago po yung selection rules, and actually the main difference, maybe it's not obvious here, but this molecule is sitting on the chlorine. So the copper is on the chlorine, but in this case, the copper is on the sodium.
I see.
So this small change in the bond between the sodium copper chlorine affects the Raman signal, I think. Can affect it. So very small change, but there is some. But basically, it's still in resonance, and it's still, I think it will still show the symmetry.
Okay. Thanks. I think we have to move on to the next speaker. Thank you very much, Raf. But before we let you go,
yes, Bob.
I would like to read this certificate of appreciation.
Oh.
There is this guy here. Okay. Kita na ba?
Yes, Bob.
All right. Allow me to read this one quickly. The Philippine American Academy of Science and Engineering presents this certificate of appreciation to Dr. Rafael B. Hakulbia for delivering the lecture entitled Tip-Enhanced Raman Spectroscopy and Imaging of a Single Molecule in Ultra-High Vacuum and Low Temperature Environments on 23rd July 2020. Should be 2020. As part of masyado ng madaming COVID. As part of the parallel session 2.2 during the 40th PAASE anniversary and 2020 APAMS, Manila, Philippines, signed by Dr. Gisela P. Concepcion, PAASE President, and myself as host. Thank you very much, Rap. You will get a hard copy of this one as soon as they allow us to go to, or you go back to the Philippines. Maraming salamat.
Salamat po.
All right, so let's move on to the next.
Wait, Raf, huwag ka alis ha. Marami pa tayong pag-uusapan.
Yan ang
Principal
purpose
office
natin.
Oo.
No problem po.
Okay, you may start sharing, Mo. I think your co-host, so you may do so. I think on your own. So the next speaker is Dr. Marianette Morales Vega. She is an associate professor and the director of the Material Science and Engineering program of the College of Science, University of the Philippines. Mo, as we fondly call her, obtained her PhD at the Graduate School of Nanotechnology, University of Trieste in Italy. In 2017, she was an Australia APEC postdoctoral fellow at the Institute for Frontier Materials, Deakin University. Her fields of interest are Raman and fluorescence spectroscopy, synthesis of magnetoplasmonic nanostructures, graphene and noble metal-based sensors, nano-hybrid materials for environmental remediation, nanotechnology, nanoparticle enhanced spectroscopy, nanomaterials characterization in general, and the more fundamental aspect of things, she's also interested in looking at magnetism and magnetic materials, which would deal on computational chemistry, in particular density functional theory. So Mo, I don't think you will have a problem with time, but it's up to you. You can take your time. So without further ado, anytime you're ready.
This will be short.
Dr. Vega, you have the floor.
Thank you. Good morning, everyone. It's nice to be awake this early to talk about my favorite topic. As mentioned, I'm from the Material Science and Engineering program of the College of Science. First off, I would like to thank these agencies and units, National Natural Sciences Research Institute, NSRI of UP Diliman, DOST PSHERD for financial support and for supporting our research for the past 2 years. Okay, so if you are wondering, bakit hindi nagmo-move ba? Okay, so if you're wondering where the Material Science and Engineering in the College of Science is, we are housed at the CSRC, the Computational Sciences Research Center, in the middle of the National Science Complex in UP Diliman. And currently, we boast of 2 equipment that are in MSEP, which is the UV-Vis spectrometer and the contact angle measurement instrument. And these are the beautiful people of MSEP. Our faculty is composed of professors from MSEP, NIP, chemistry, and there are affiliate units who advises students, MSE students from these institutes, NIP, chemistry, IESM, and NIMBB from history, I think. So this was taken in our last year-end party. So hopefully we can have another party like this in the future. I have started forming a small group and I am the smallest in this group, the nanospectroscopy group. And we are, what we do currently, at least for a start, we try to find nanoparticle-based solutions for some prevalent problems. It can range up to environmental monitoring, some detection of contaminants in water, and we synthesize different types of nanoparticles. It could be in the form of spheres and rods, and also you will see later on some anisotropic shapes of nanoparticles. So these two gentlemen here are graduating hopefully very soon in a couple of days. They will be defending their master's thesis. So medyo mababawasan kami, but hopefully some new students will be joining. Okay, so our main weapon for annihilation, as I would always say to my students, is gold nanoparticles. So it's ubiquitous in most applications in biomedical, even in electronic applications, because it's very easy to synthesize and it's very versatile in the sense that you can attach several entities on the surface and it can perform a particular application. So a range of materials that you can adhere on the surface of the gold nanoparticle could range from proteins, DNA, lipids, and depending on your application, you can customize or functionalize it with these types of molecules. The main advantage, if you're not familiar yet, it has very remarkable properties in the nanoscale and very different from its bulk counterpart. And as I've said, it's very easy to make, cost effective, and in most applications that we use gold, we only use very little. So it can last us several years for just 1 gram. It's highly tunable. You can, by simple modifications in the synthesis process, you can change the shape, and each shape would give you a particular property, specialized properties in its in optical terms. It's also used in biomedical applications because it's biologically benign. You can practically drink gold nanoparticles, but don't do that. It's stable in aqueous solution. That's why it can be used for biological samples. And since it will be in solution in most applications, it could serve as a buffer or to protect the sample from photodegradation. And as I've mentioned earlier, it can be functionalized in several ways. So some applications that utilizes gold would be, I think the most important here, I think, would be hyperthermia in cancer therapy. So these are being injected in rats now for clinical testing, and then it heats up the tumor locally, and then it kills a particular site of the cell, not the whole tissue. And catalysts also, it has a very high efficiency in conversion of different gases and acids. The one particular application that I'm interested in now, so we did direct our research in these types of applications, is on diagnostics. So this is an ambitious application, which is the early detection of dengue, and also our recent situation is the SARS-CoV-2. So hopefully there are configurations now that utilizes gold nanoparticles for detection. So what's remarkable about gold nanospheres is that its ability to change its color, the perceived color, just by changing the size. So, and you will see later on that if you change the shape also, the color that it transmits would also be different. So it's being utilized also for diagnostics because some molecules causes gold nanoparticles to aggregate. So the changes in color would signify the presence of these types of molecules. So that's how it's being used as a sensor. Ito, this this is a typical absorption spectrum of gold nanoparticle solution with a mean diameter of 10 nanometers. And all my students already know this by heart, that if you measure it in the UV-vis spectrometer, it will absorb at around 520 nanometers. And it changes when some morphological changes happen in the gold. So thank you, Raf, for giving the introduction on the Raman spectroscopy. So I don't have to do it now. So in our applications, the main tool for detection, apart from having the nanoparticles, it is coupled with the Raman spectrometer. And as mentioned earlier, it tracks the changes in the energy that is scattered from, that is provided by the vibrational modes of the sample. A modification of that, since this is a very weak phenomenon, one way to work around this weak signal is, the first technique is the TERS, and then another technique would be the SERS, the surface enhanced Raman spectrometer. This doesn't make use of the STM. It is the same Raman technique, but when you add nanoparticles in them, the resulting scattered Raman signal is significantly enhanced. And there are reports that it could be enlarged by 10 to the 8 experimentally, 10 to the 15 theoretically. And one example that I placed here is that a very small concentration of mercaptopropionic acid is measured using Raman. And if we put the nanoparticles in the solution, so by the way, this is a solution measurement, wet sample, wet drop that is being measured, then all the signals or the significant modes are enhanced. 2 nanomolar concentration is small in bulk point of view. So it's not quite single molecule, but it's already acceptable for solutions measurements. So just to illustrate, it has been demonstrated that for patients that are infected with dengue, would show a markedly different Raman spectra compared to a blood of a healthy person. So we would like to bank on this phenomenon in detecting the infection earlier in or at the onset. So we are talking about concentrations lower than 2 nanomolar of the infected of the infection. So in this way, what we are modifying is not the technique, but the type of substrate. So the metallic nanoparticle that will be in the vicinity of the molecule that you want to detect. So we are synthesizing various morphologies and trying to come up with the optimized configuration that will give us the biggest enhancement in the Raman. So the most sophisticated that we have synthesized is the gold nanostars. And the reason for studying these types of anisotropic nanoparticles is due to the presence of the hotspots. So when you use spheres, you generate this small region of high electromagnetic field at the junctions of the spheres. And so when you measure Raman, you would want your nanoparticles to aggregate at not so much, but only a little bit. And the most ideal would be the dimers. But in the case of nanostars, you don't rely on the aggregation of the nanoparticles. A single nanostar could give you several points of hotspots, as you can see at the bright spots at the tips, and it occurs at the tips. And just to emphasize that the highly tunable nature of these nanostars, you can change the optical properties by making the spikes longer, thinner, and this will just be brought about by the changes in the synthesis process. Just very easy. But one thing that we have seen in this study is that it's not stable for long periods of time. So it experiences aging. And as you know, if your substrate changes its optical properties, it will affect its Raman response. And to illustrate that, these are Raman spectra of the pure mercaptoethanol, also at very small concentration. You can see there is no signal to speak of. This is actually a signal from water. If you use nanostars that have longer tips, you get a little bit of response, but it becomes optimized when you have nanostars that are in the mid-range, intermediate length, not blunt as a nano popcorn, but midway between a very sharp tip and the one that gives you wavelength maximum of 689. So we are seeing here, this is one example that there is a threshold of the maximum enhancement that can be produced with these nanoparticles or nanostars. So this is what we are trying to investigate more systematically. Since this suffers in degradation, or it morphs into popcorn, and we do not want that to happen. So there should be a way to protect the surface from changing. And so I have found that coating it with a single monolayer of mercaptopropionic acid extends its lifetime by up to 1 year, which is a huge achievement, because if you have synthesized these types of narrow structures, they're very unstable. So they would really want to go into a sphere formation. Okay. So as you've noticed here, in the previous slides, we are investigating solutions. So that is the advantage of SIRS. You can measure molecules in solution form, even in wet drops, which I have to ask Raf if it's possible for STM. But very little literature is present in using the SIRS technique, so liquid colloidal substrates, on detection of highly dense solid samples. So the model system that I had the opportunity of testing, because this is part of another project. I was tasked to find a certain structure of zirconia in a dense stabilized zirconia sample that are being used for biomedical implants. So spinal discs, this is a ball joint hip replacement, and these are the ones that are used for dental implants. So we could all appreciate the succeeding slides. The stabilized form of zirconia is in the tetragonal structure. So this is the spectrum that is expected. When it is exposed in high humidity environment, it changes a little bit in a monoclinic structure. And this entails a about 5% increase in volume. So if you could imagine, if it's inside your body, and then it changes structure just because it's in a humid environment exposed to water, there would be cracking that will occur if this changes its structure. So the Raman spectrum of such structure, monoclinic, is given in this bottom spectrum. So a crazy idea came that what if I use SIRS on these types of application, finding a monoclinic structure in a sea of all tetragonals. So I was skeptical at first that this will work, but I have to graduate, so I have to make it work. So here, this is a sample of a spinal disc, and the normal Raman, just to compare it with the SIRS effect, I measured a particular area, a small area with a normal Raman in confocal mode, and then drop the substrate on that same area and then measure the SIRS signal afterwards. And this is what I found. So remember that when it's in tetragonal, you want two that are in the 140 and 275. And just by looking at that face value, you don't see a lot of difference. But by the way, the nanostars that were used here gives you an absorbance maximum at 690. So that's an intermediate size of spike. But if you focus into the standard deviation of the plots, then you see some activity happening in the range where you would want the monoclinic peaks to appear. So that's between 190 to 200, or maybe a little wider, 180 to 200. So now it's starting to appear. This is a clean surface without nanostars, and then on the right will be the surface with nanostars. And if we take the total area under the curve of those spectra, then it becomes more evident that in this region where the bright line appears would be the position of the ones that have transformed from tetragonal to monoclinic. And this is quite an achievement because we are talking about 2 volume% of monoclinic sample, monoclinic phase in the whole implant. So in bulk terms, again, this is almost single molecule level. It's very hard to find this kinds of structure. Okay, so as a summary, and I will also be mentioning some of the future work that we are doing regarding these topics. The synthesis of nanostars is always a challenge. It's hard to find a surfactant that will allow us to stabilize the nanostars in solution for several months. At the same time, the surfactant should also allow the penetration of the incident light and give you still a higher Raman signal. And that will only happen if the hydrocarbon chains are very small or short, so that it still it still has access to the metallic surface. But then this is a relatively short hydrocarbon chain for mercaptopropionic acid, and it exhibits long-term stability over 1 year. And hopefully, just on this topic, we could find other surfactants that could do the same. And in this one, so we have shown that it is possible to use the technique surface enhanced Raman in a solid surface of an insulator that is highly dense and polished. So not only for porous powders, not only for solutions in molecules in solutions, and yeah, we would like to do more experiments on this, probably with another material that is of importance in other fields. And as an outlook, um, Inters, Raf has mentioned that it is a resonant technique, but for SIRS, it is not always true that the highest Raman enhancement would be achieved when the incident light is the same as the absorption of the metallic surface. The general rule, but it is not supported well enough by experiment, is that the excitation wavelength should be straddled in between the absorbance wavelength and the mode that you are trying to detect. And so, and this is the point that we want to clarify in most of our experiments. My student, Joven Angeles, will be clarifying on this tomorrow. So you can check out his presentation so that we would know uh, something about this. And also, we have also investigated growing the nanostars on 2D materials. Again, one of my students, Gil Cabrera, will be presenting on this topic kailan ba? On Monday. So watch out for those presentations. So I guess that's it for me. I initially wanted to present their results, but I changed my mind because I didn't want to steal their limelight when they present it for the first time tomorrow and on Monday. So just watch out for their presentation. A little what do you call this, plugging, commercial. So if you are interested in these types of research, we are open for studentships in our laboratory, and you get to synthesize sophisticated shapes of nanoparticles, be it silver or gold. And yes, yan. Oh, nami-miss ko na kayo. Hope to see you again. Thank you.
Thanks, Mo. Dami na pala. These are your students or students
I
in general?
know. Ano to? We held our poster presentations for the lab classes.
I see.
Ceramics and electric and magnetic measurements lab.
I see. Nga pala. Okay. Questions from the audience?
Meron pa bang next yan? Wala na. Okay.
So we have time for 1 or 2, even 3 questions.
Short lang ba? Sana
you may raise your hand or you may unmute yourself.
Elmer?
Good morning, Sir Al. Good morning po.
Good morning po.
Yeah, good morning. Very interesting work, Mo. I didn't even know that you got... clearly, I used to work for implant and artificial skin. So yung silver impregnation on microbial cellulose would be a very interesting project right there for antimicrobial properties. Okay. But not all silver are equal. So pwede na natin gawin yun tomorrow. I have microbial cellulose, biocompatible and implantable. So pwede mo nang gawin yun. Bigyan kita ng materials bukas.
May mga silver na po kami. Nandun lang. Nakaimbak lang.
Ayun. Pwede na tayo magsama doon. So that's one. That's for
thank you.
both topical and implantable. And since my material is the same material as Nata de Coco, we have abundant supply of materials if we go production scale. But it's a nanoscale nanofiber, about 140 nanometers. But the one that I asked a question earlier is I'm working with Wendell Rivera, who's the newly inducted sa NAST. He is interested. He developed a methodology for dengue saliva detection. I'm helping him to develop a saliva detection for COVID-19. Clearly, the most of the laminar flow antibody rapid detection is now being done on gold particles. That's partly your work as well. I don't know yet how it will be. I'm talking to Singapore later this afternoon to get the actual antigen antibody supply for potential detection. These are the specific ones that are for antibodies produced against COVID-19. So it dawned on me that we can use your particles and we can detect it with Raman. Of course, you'll have to compete with Elmer. We're working on terahertz detection naman with Elmer, at least all on a conceptual basis. But again, any non-biological with some biological combination of confirmation. I'm trying to avoid kasi the double detection that's being done right now, antibody plus RT-PCR pa.
Oo
So,
nga
tapos
po.
hindi ka pa sigurado sa viral load. So I'm trying to solve this whole get back to work COVID-19 detection. So if we can say that you have no virus and you have the antibody, go back to work. So I need two types of detection, a biological and a physical. So kay Elmer looks like are the potential physical testing, may it be terahertz, may it be Raman. Again, we might have to attach it to a gold particle if need be to enhance the concentration of the antigen that you're trying to detect or the antibody. But it's something that I'm very open to discuss and collaborate with your group now that I see what you're doing.
Yes, sir.
Is that
Thank you po.
possible?
Of course. Very welcome.
Nasaan ba yung lab
And
mo? Are you in the triple M or are you in
nasa
the computer
CSRC
science?
po. Nasa CSRC, but of course, Dr. Estacio is very generous in sharing
naman.
the laboratory with us as well.
Yeah. Sir Al. Sir Al, hello. Okay na ba? Sir Al, Mo heads the Material Science Engineering Program of the College of Science. Dalawa po
Yes.
kasi yung Material Science Engineering Program ng UP Diliman. Both are
Okay.
graduate programs and both hand out their own diplomas. Kasi silang magkaibang degree. One is under the Met and Mining.
Okay,
And,
yeah, that's the one with Leslie.
Yes po, exactly. And there is a program that is co-implemented by the College of Science. This Mo heads this program. Graduate program.
Okay. That's very good. Nasaan yung lab? Are you in
Sir,
that
nandun po
complex?
sa mismong complex. Nasa gitna actually. Nasa likod ng opisina ni Gani. Yung
Yes.
kaduplex
Okay.
na building. Yung kaduplex na building.
Sadyain kita pag bisita kay Gani next week.
Sure.
Or the following week.
Opo, sabihan niyo ako so I may also be able to catch up with you.
Yes.
Yeah, let's all meet together. Definitely.
Okay po.
Dr.
Thank you very
Sir Africa
much.
is too modest to introduce himself.
Never mind. Okay na yan. Well,
Sige po, Sir Al.
we'll
Maraming
link it.
salamat po. Thank you very much.
Thank you, Amber. Thank you, Mo.
Thank you po. And good news po, gold can also be used with terahertz. So talagang pwedeng combination.
Alright. Thank you. Nice to know. Usap tayo. Any other
Ayun.
questions from the audience?
Tulungan natin si Elmer. Nakama-detect ni Elmer yung COVID-19.
Thank you po. If there are
Okay.
no more questions, sige, sir. Before I let you go, Mo?
Ay,
Sige, sandali lang ha. Mayroon tayong customary sharing of screens. Yun. And I would just like to read this. PAASE APAMS presents the certificate of appreciation to Marianette B. Morales Vega for delivering the lecture entitled Gold Nanoparticles as Substrates for Surface Enhanced Raman Spectroscopy on the 23rd July 2020, tama ng taon, as part of Parallel Session 2.2 during the 40th PAASE anniversary and 2020 APAMS, Manila, Philippines, signed Dr. Gisela P. Concepcion, PAASE President, and myself. So thank you very much, Mo.
thank you also for the invitation. It's an honor
Hoping
to present.
work with you guys in the very near future. So let's move on to...
Thank you.
Thank you, Mo. Wait lang po. Before we welcome Dr. Hermosa, I was requested by Dr. Concepcion magkaroon tayo ng konting attendance. How do I go about this one?
Sa chat na lang, name.
I think I have to May I request everyone to please turn on, even for a brief moment, momentarily turn on your videos. Quickly, don't be shy.
Yeah. Pakita kayo. Kahit
Oops.
hindi pa kayo naliligo.
Morning, everyone. I-pass na siguro natin si Ma'am. I'm sure she's very busy. Si Ma'am Giselle.
Yeah, pero palagi kami nagpo-photo op pag
Ay, oo nga pala.
Bida,
hindi para magbilangan.
mag-roll
Tapos
call ako.
maninigil niya si Giselle ng membership.
I'm sure. I'm sure.
Camille.
Oh, bakit? Ang shy naman ng ating audience. Walang gusto magpakita.
Sai.
Jackie.
Ayaw nila.
Nagro-roll call.
All right, probably we can start. Yung pag wala
Ayan,
tayong magagawa pag walang camera.
Nag-screenshot
Paano
na.
kayo magiging assistant,
Okay na?
associate at saka full member sa PAASE kung hindi kayo nagpapakita?
One more, the second page. Okay. Thank you very much. All right, you may turn off. You may turn off your
Nasa si
cameras
Giselle?
now. Busy po yata, sir.
Hindi, nandiyan nakakasama sa participants
Kaya nga po, busy po yata. Hindi nag-on ng camera. Nakamute din si ma'am.
Siya pa yung nag-request. Sige, okay na.
Thank you very much, sir. Thank you po.
Thank you, thank you.
Ay, nandiyan si ma'am. Hello, ma'am. Good morning.
Okay na. Ayan, sama niyo si Giselle.
Oo. Well, pinamonitor ko lang lahat kasi interesado rin ako dun sa neuroscience ni Vince Daria, brain.
Yeah, hati nga
Doon
But
naman
mas
sa
malapit kay...
geology, yung speaker from Caltech and NASA, yung mga yung mga the abiotic rock contribution to life, no? And I have this interest in methanotrophic bacteria, our rock-eating shipworms. But anyway, I heard you, Al, regarding our desire to develop a diagnostic. There are already COVID-19 diagnostics based on gold nanoparticles. Yes, there are.
Marami, pero we're going to do terahertz or Raman spectroscopy, Giselle.
Yeah, and Raman spectroscopy pati. Part, no? Pero yung kay Dr. Vega, interesante pala.
Exactly.
Saliva, coupled with the saliva.
Yeah,
okay.
We're meeting Singapore with Wendell this afternoon.
Wonderful. Great.
So we'll get it going, lady.
The three parallels are going so well. And I am the cell phone, the desktop, and the laptop.
Tatlo. Ako naman iPad, iPhone at computer.
So Elmer, everyone, thank you so much. Sige, I'm continuing to.
Thank you very much for your support, ma'am.
Okay, bye-bye.
Everyone, that's Dr. Giselle Concepcion, our president. Thank you for gracing us with your presence.
So important. Thank you.
Thank you very much, ma'am. Okay, so let's move on to the last, but definitely not the least.
Not the least.
Yes, po. So, Dr. Nathaniel P. Hermosa is going to talk about structured light. Let me just switch this to Nath. You may start sharing your anytime. So for the last speaker of the session, we have Dr. Nathaniel P. Hermosa. He's a full professor of the National Institute of Physics, College of Science, University of the Philippines, Diliman, and he's currently the Institute's Deputy Director for Academic Affairs. We all know he is very, very busy right now with all of these changes going to switching to online academic format that's going on. And he's the group leader of the Structured Light Group at the Photonics Research Laboratory, where he is currently an advisor to 6 PhD, 2 masters, and 2 BS students. His fields of interest are optics and structured light. Nath obtained his PhD in physics degree at the National Institute of Physics and did postdoctoral research work at the Higgins Laboratory in Leiden University from 2009 to 2011. And then, please correct me if I'm wrong, Nath, Institut de Ciencias, Photonics, Spain, 2012 to 2014, and came back to the Philippines as a long-term, balik PhD and DOST Balik scientist, and has since been a member of the National Institute of Physics faculty. He has recently got an award as the one of the UP Professorial Chair for Outstanding Teaching and Research, also a Scientist One awardee, chosen as the Asian Scientist Magazine Top 100, NAST Outstanding Young Scientist Award, and Third World Academy of Science Prize for Young Scientists in the Philippines 2017, and lastly, the Eduardo Quisumbing Medal for Outstanding Research and Development for Basic Research, also in 2017. So to talk about, the title of the talk is Structured Light Optics for Engineering and Automation. I think that, okay, pre-recorded this video, but of course that is with us right now. So you may ask questions afterwards. So Nat, please, you may start.
Okay, good morning. I'd like to share this video. Can you hear me?
Yes, we can. We can.
Okay. Now, I pre-recorded this video because my computer, my internet has not been very good this couple of days. I feel so out of place with the discussion with the Raman spectroscopy. I should have given another talk, maybe the materials part of my presentation, my research. But here goes the structured light for engineering and automation. Okay. Can you?
That's all right. Okay lang yan.
Good morning. I am
Yep.
Nat Hermosa, and this is my presentation. I started playing with the shapes of lights in 1999. This is an LG01 I got from printing out a hologram in a laser printer back then. The research started with Dr. Taroha Keller, and she's looking at the dynamics of these modes in a laser cavity. So what was the intention during the time was to get one of these beams inside a cavity and look at how it interacts with a nonlinear crystal in that cavity and see how this beam evolves. But the current state that I will be presenting now is very different from her applications before, wherein she wants to look at the chaos, the dynamics of laser modes. I want it to be more applicable to engineering. My title is Structured Light Optics for Engineering and Automation. I am Nat Hermosa. And with me, this is the work of Catherine Isabel Remulla, Jads Princeton Narag, Nina Zambale, JC Lorenzo, and Miara Tolentino. We're from the National Institute of Physics, University of the Philippines in Diliman. I have to apologize that I limited this talk from the abstract that I sent to Dr. Estacio because of time. What is this talk about? This talk is about diffraction and hopefully some clever ways to apply it. If you think of diffraction, you always think of these two people, Agustin Jean Fresnel and Thomas Young. Of course, Agustin Jean Fresnel is French and Thomas Young is British. Thomas Young is much older than, not really much older, but older than Agustin Fresnel, and he qualitatively described diffraction of light by an aperture as a superposition of geometric wave and boundary wave that scatters from the edge of the aperture. Initially, Agustin Jean Fresnel would work on this, but he got frustrated. So he developed his own definition of diffraction. Fresnel thought of diffraction as a superposition of imaginary sources from the aperture. Now, the definition of diffraction that we currently use now is due to Fresnel. Most commonly used now is due to Fresnel. But in this talk, I will be discussing the diffraction as described by Thomas Young and see if that could help us and that could be beneficial to some application. Later on, okay, this was in the they did it in the 18th century. Fresnel and Thomas Young did it in defined diffraction during the time. But in 1888 and 1924, or the 19th century, or the 30th and 20th century, the Kirchhoff-Fresnel diffraction integral over the aperture was reduced, or can be reduced, to a line integral over the boundary or the rim of the aperture. What does that mean? It means that that basically Fresnel's and Young's diffractions are similar. If you look at the aperture. It's just that the diffraction of Fresnel, or the mathematics for the diffraction of Fresnel, came earlier than that of Thomas Young. Remember, Thomas Young did not do mathematics, he just qualitatively described it. So again, let's go back to Thomas Young's diffraction. In Thomas Young's diffraction, he looks at the geometry of the aperture. He says that the apertures consist of two waves. Okay, one is a geometric wave that takes the shape of the geometry of the aperture, and the second is a boundary wave that emanates on the boundary of this aperture. The wave that emanates from the boundary of the aperture is pi shifted with respect to the geometric waves. It's a very important fact. So what is the fuss about? Well, it is interesting that until now, we still look for inspiration for research from work done more than 2 centuries ago. But to me, and in this talk, we'd like to find a more computationally easy way to handle some features of diffraction that can be useful to vision and engineering. For example, in this talk, how do you distinguish a circle from an oblong? Well, we know this for a fact. When we were young, we were taught that what a circle is and what an oblong is, right? But what if the eccentricities, or the way that it elongates, is very small, so that you cannot distinguish by eye between a circle and an oblong? Similarly, we want to distinguish between a triangle and a square, or a slit whose triangle and slit is a square. Again, we know this fact. When we were younger, we were taught this. But when you have a machine, how do you tell a machine which is a square and which is a triangle? Well, you have several algorithms happening now. But can diffraction help in in making that algorithm a lot faster? And lastly, well, this is the last part of my talk, is what happens when aperture rotates? Is there a way to measure its rotation or its velocity as it rotates? Well, you can use a fast camera. That would be no problem. If it's so fast, maybe you buy more expensive camera to do it. But see, we develop a way such that you don't need a camera, you just need a photo detector. In this talk, I will discuss how progress in the fundamental understanding of optics could offer solutions to some problems in engineering and automation, exploiting advantageous properties of light, such as the speed of transmitting data and its sensitivity under perturbation. The outline will be based on this talk: the tilt angle alignment, diffraction of polygonal slits, and rotational movement, and I will summarize this after. Tilt angle alignment. Okay, I have here a cone in a picture in your right. There's a cone there, and if you see the person with the green eyelashes, just straight to it, you see it's seeing a circle. But if you notice the other person with eyelashes of orange or yellow, it's tilted. So it sees an ellipse. The circle for the green person is different, is ellipse to the person with yellow eyelids. This is how we determine, by looking at the shape, we will know the tilt of a circle, if it's tilted or not. So this is how we align the tilt angle. If you go back to papers, the initial papers doing this, you find out that in 1922, in the Physical Review paper in 1922, Coulson and Becknell already look at this problem. They say that if you look at the evolute of the aperture, you will be able to know where the maximum intensity will appear. Okay? Where, at what places will the maximum intensity appear? The evolute is its locus of the centers of curvature. It is given by the equation on the right. Equivalently, the evolute can also be imagined as the envelope of the tangent lines to a curve. Now, let me explain this. Okay, this is their experiment. What they did is to machine apertures, circle, ellipse, or oblongs, and then they look at the intensity at the center. As you can see, even if 1 and 2, for example, look like they are both circular, they're not. If you notice, 1 is a dot, and the 2 is in an asteroid. We call it an asteroid. You see, an evolute of a circle is a dot. The evolute of an ellipse is an asteroid, whose elongation depends on where the oblong is elongated or squeezed. Now, in geometric wave, we say that, okay, we have a beam that's directly the bright region that goes out of the aperture, and the boundary wave that is given by this equation. If you solve for R, if you decompose R, you can find an X and Y parameterized with T. It's just a parameter T, and you can get the evolute of this function. And there you'd see that you have a circle, you have an ellipse, and you can think of it as a tilt. Now we go back to our expression. Instead of just using apertures, what we do is we use a slit. Why is a slit important? Why is slit more significant to us? Well, a slit can be thought of as two waves. Say psi A plus psi A prime, and this psi A is a combination of a geometric wave and a boundary wave. Similarly, a psi A prime is a combination of a geometric wave and a boundary wave. Now, to construct the slit, what we do is to subtract these two. If the geometric wave of the bigger aperture minus the smaller aperture is similar, then the intensity will just be given by the boundary wave. And to measure that boundary wave, we also have to, well, we just look at the evolutes. This is what we got from simulation. You see, the oblong here is squeezed in the x-axis, so therefore its asteroid will be much longer in the x-axis. Similarly, if it's squeezed on the y-axis, then its asteroid is elongated in the y-axis. The thing is, at the center, if you have a circle, the evolute of a circle is a dot. So therefore, you'd see that you have a very perfect dot at the center. So we did an experiment. It's nice that we have what you call a digital micromirror device, because a digital micromirror device, you can dynamically control the flipping of the lenses of the mirror. Sorry, it's composed of 600 to 800, 800 by 800 micromirrors. When you put a pixel that's equivalent to white, it flips in positive 12. When you put a pixel that's equivalent to dark, then it flips to the other side. So it puts the other intensity to the other side, so that you can't see it. The thing with this DMD is that it has inherent misalignment. It has inherent elongation. Why? Because it is diamond in shape, not square. So because of this inherent diamond shape, a square that you input in your DMD becomes a rectangle, as you can see from the figure below. So this is a nice way to experiment or to verify the things that we were discussing earlier. Now, our experiment is very simple. We just put a Henny laser. We filter because it's too bright. We expand, and then we put it in the DMD and look at the scaling, the X and Y. The S here is the ratio between the Y and the X axis. As you can see, they look the same. The apertures, when the figure, the images, when we upload to the DMD, look the same. However, because they have different aspect ratios, they produce different patterns. As you can see here below, 1.7, or a ratio of Y versus X of 1.7 produces an asteroid. Similarly, a ratio of 2.1 versus 2.1 produces an asteroid. And a good ratio of 1.9 produces that dot at the center. And here we know that we can correct for the misalignment in your DMD. This topological changes from a dot to an asteroid is very drastic, that results to a sensitive method of determining the scaling ratio. The scaling of a DMD depends on the pixel size spacing and also the alignment of the system. The fast determination of the aspect ratio of the DMD is significant, especially in beam shaping applications, or in this talk, you see it's significant in knowing what a circle and an oblong is. We just look at the diffraction. The second part is diffraction of polygonal slits. Now, it's a little bit tricky because if we go back to our construction of boundary waves, the intensity pattern is just equivalent to your boundary waves. The evolute given evolute of R parameterized in X and Y. However, if it's a polygon, it does not make sense. It's infinity. What is the evolute of a polygon? You cannot have a value, and that is a big problem. The evolute of a polygon is undefined. All right? Let me give you the equation of the evolute. We solve this problem by defining another evolute, or what we call a second order evolute for a polygon as. So we take the ratio of Y over X and approach the X double prime, or the second derivative, and the second derivative of Y approaches to 0. And what we got is an X prime over a Y prime that's equivalent to just 1 over a constant. It means that the evolute becomes a line that is perpendicular to a side of the polygonal slit. What does it mean? It means that for a triangle, you have 1, here is the 1, here's the slit, 2, and there's a slit here, 3. If you add them together, you have 1, 2, and 3. And this is your evolute. These are the regions of high intensities. Similarly with the square, the 1, 2, 3, and 4. Say 1 and 2. And that would give you, well, X and X, 1 and 2 high intensity patterns. And then it's go on to pentagon, hexagon, and other polygons. So we did an experiment, and indeed we got high intensities for the triangle, 1, 2, 3, 1, 2 for square, and so on and so forth. The evolute becomes a line that is perpendicular to a side of the polygonal slit. Okay, so what do we know about this? We show that for polygonal slits, only the boundary waves contribute to the diffraction. From this, we obtain the brightest regions of the diffraction in the perspective of catastrophe optics by taking the second-order evolutes of the polygon. So now we can determine, by using boundary wave diffraction theory, a square from a triangle. Now, it looks like a lot of job for determining a square in a triangle, because we know how to do it by, well, we studied these shapes when we were very young. But again, let me remind you, when you're teaching a machine, for example, to determine a square and a triangle, you have to get that unique property of what makes it a triangle and a square. And we say that this diffraction, or by looking at the boundary wave diffraction theory, could give us some clue on how to input that and make it a good sensor for a triangle or for a square. Lastly, I'd like to end this with rotation measurement. How can we measure fast rotating object? Again, if it's very slow like this one, well, you can take a picture, you can use your eyes. But it becomes very fast, then you wouldn't know how fast it is. There is a limit to our eye, and there's a limit to the refresh rate of a camera. Of course, you can buy better cameras, but that would be too expensive. So our solution is, again, we'll go back to a boundary wave. This is a paper in American Journal of Physics in 1987, sorry. What it does is it looks at the double slit experiment. Okay, let me remind you again of what the double slit experiment is. A laser beam, for example, impinges on a double slit in the figure in the right. No? And what you see in the double slit at the far field, at the far distance, is that at the center of this double slit, or near, you see the bright bands, and then succeeding to it, you see the alternating bright and dark bands. So Ganchi wanted to know if the boundary wave that Thomas Young was saying is physical. So what he did is to put a block at the beam, a laser beam. So you have an aperture, and this aperture emanates a pi shift. And he lets it impinge on his double slit. What happens is that instead of getting a bright band at the center, he gets a dark band at the center. Now, what does it mean? It means that this beam that comes out of that block is a combination of a beam which has a pi shift and there's a pi shifted from the original beam. So that is a good experiment on, well, realization of the boundary wave as pi shifted. Now, what if, for example, I change this laser into an HG01 mode? An HG01 mode can be done with a spatial light modulator. If I place it with an HG01 mode, okay, the HG01 mode has the one lobe is could be a reference phase, and the other lobe is usually is pi shifted from the first lobe. So the beam looks like this. If I block it, right? If I block it, we say that if we block it, it becomes the boundary wave becomes pi. It gets a pi shift. Below, it's pi, so it adds another pi. It becomes 2 pi. But if you look at the center, because this pi and 2 pi interfere, and their phase shift between them is pi, then you have a destructive interference. So at the center, you wouldn't see any light. Okay? What if I rotate it? Say this one. Again, it blocks the reference phase at the first lobe. And because you have an edge, it emanates pi. So pi and pi, and it interferes with the pi shifted, with the phi phase at the bottom. It produces constructive interference. So therefore, you have bright at the center, the far field. So you go back and do this a lot, left and right, and then you rotate it. In the end, you'll have something like this: a power and time versus rotational position. So if it's rotating, you could see that sometimes it's low, sometimes it's maximum, sometimes it's low, sometimes it's maximum. And you only look at the center of the beam. In the parlance of people who are doing this now, it's called, okay, so do this and do this. Mode projection. What is the equation of this mode projection? If you look at this, this HG is our input beam. This tau theta is the one that's rotating. And this GX here is your Gaussian mode, whose proxy is this very small area where you are calculating or getting the intensity from. Okay? So again, rotate. Here, it's pi, it's maximum. If it's rotating, then you'd see that it should follow a sinusoidal pattern. We did this experiment with a tunable laser beam, tunable laser, different wavelengths. We put SLM, and in SLM, we aperture the SLM going out, or we remove other intensity to approximate that of an aperture. And then we put the mode that we wanted, the HG mode in our SLM to produce that HG mode. And in this case, we use a beam provider, but a photodetector that has a pinhole could work as well. So the power, as you rotate it, becomes the other. Now, you may think that we have a theory for this, of course. We calculated the equation earlier, and it's quite straightforward. We just have to use orthogonality condition, and you come up with this theory curve. We did experiment for HG01, and we know that, well, based on boundary wave diffraction theory, that you can have some things. You could see a sinusoidal power, and it's also based on solving this equation. You can have that sinusoidal power. But if you use an HG11 in your SLM, you'll have zero power, or very low power. And this result is in preparation. In summary, we show that the boundary wave diffraction theory, we show that by boundary wave diffraction theory, it is possible to determine the rotation of a half circle aperture by shining it with the proper beam mode. Okay. So what's the whole thing about? We use the boundary wave theory, as I've said, qualitatively developed by Thomas Young in the 18th century to solve problems that are important in vision engineering. You see that we can distinguish circle from oblong, we can distinguish from a rectangle, a square from a triangle. These are corrections of alignment, polygonal shape determination, and getting rotational motion. The thing is that in this talk, I'd like to say that by looking back and understanding fundamental concept in optics, we can have engineering processes that can be a lot faster. To live, they say to live to the future, one needs to find inspiration in the past. I'd like to end this talk with this work by Becknell and Colston in Physical Review 1922. What they do is to look at the cardioid and see the diffraction of the cardioid. If you find the evolute of the cardioid, you'd know that the evolute of a cardioid is a circle. And they said that in that circle, they find the darkest region. We still need to verify this, and I have a hunch that this is correct, is that at the heart, at the center of a heart, is actually a vortex. I got my funding from the University of the Philippines Office of the Vice President for Academic Affairs and the Office of the Vice Chancellor for Research and Development of the University of the Philippines in Diliman. I also got funding from the Philippine Council for Industry, Energy, and Emerging Technology Research and Development. Thank you very much. Okay, that's my presentation.
Thank you very much. Actually, the session ends officially at 10:30, but the Zoom session that we have reserved is, I think, for 4 hours or so. So we do have time. If you need to be elsewhere and you want to ask a question, we may prioritize you kung sino may gusto magtanong. But for those who want to stay and chat with us some more, we'll be here. So questions from the audience?
Taning.
Ayan,
Quick one lang.
Okay, sige. Would it be all right, Jackie, punahin natin si Sir Al?
Yes.
Thank you, Jackie. Sir Al, go.
Yeah, just quick lang, just a plug. We had an extended discussion with Romel Gomez yesterday about the remote laboratory for physics and chemistry. I don't know if you were in the plenary yesterday, but we need more input from the local scientists. So maybe I'll recruit you in terms of being able to design. This is the VISR 2 of your Dean Gani's. VISR 2 is now going to be put in the cloud, and we need to design the experiment for the post-COVID era in physics and in chemistry and biology. I have takers in Sean, academician Sean, and LB wants to do biology, and Babylin, Dean Babylin of engineering, wants to do engineering, but I'm looking for physics and chemistry. So maybe I know you're part of the physics group on education, so maybe it might be a good project with NAST and PAASE. That's it. I'm just plugging it in. If you're interested, just let me know.
Thank you for the invitation.
So if with your permission, we can actually have this
officially
announced at NIP
to
the DDAA, and probably we can have it an institute-wide activity if it's fine. Mas efficient po kami magtrabaho as an institute kaysa pagkaisa-isa.
Yes.
To the director. Thank you very much, Sir Al. Yes, Ma'am Jackie. Please go ahead.
I have a question because your rotational misalignment, that reminds me very much of edge detection in phase contrast microscopy or spiral phase contrast. If you think, actually, can I share my screen? Pwede ko ba yung gawin? Hindi.
Sure.
Hindi disable.
Pwede ka namin gawing host. Sandali lang siya.
Oh, sige, okay.
Won't take long. Done.
There. You can now share.
You can now share screen.
So, i-share ko lang to. Kasi parang ano siya eh. Yung sa'yo, yung object yung nagro-rotate, di ba?
Yes.
Dito sa sinishare ko, ang nagro-rotate yung light. So, pwede mong i-detect yung mga edges. So, this is actually simulation lang to that. Pero Mandelbrot set yan. So, actually, mahirap yan. Tingin ko mahirap siya gawin.
Yes.
experimentally, pero it's one application of what you're doing. Kung mahirap, kung gusto mong mag-detect ng edges sa transparent.
Paano rotation yan, Jack? Linearly polarized tapos may halfway plate ka or elliptically polarized siya?
And ano to, parang yung kay Nat lang. So same polarization pero ano siya, may phase step.
0 and pi.
I see.
Tapos iikot mo siya.
Ikutin mo.
Kaya ng half lambda.
So
Hindi.
mismong
ano.
Yung mismo,
parang sa SLM, yes.
Parang sa SLM, yung exact.
I see.
Ikot mo yung SLM.
Okay.
Tapos pag isa-scan mo siya dun sa object mo na transparent pero may face edges, madidetect mo yung mga.
But this is your experiment, Jack.
Hindi ko, simulation to. Hindi namin ginawa yung experiment. Pero imaging, pwede mo siya gamitin for imaging.
Yeah,
so put things in perspective, Jackie, would you give us an idea how big these structures are? Jack?
Simulation lang yung pinakita ko. Huwag kayong...
Yeah, but...
Pero yung setup niya. So parang yung point spread function ng microscope mo.
Maliit. So maliliit to kung point spread function yan.
Ito, yes. Pero
anong dimensions yan?
Na-scan mo siya dun sa object mo.
Okay.
Pero hindi ko alam kung useful siya sa industry, pero just something to think of in your toolbox kasi kaya mo na siyang gawin sa ginagawa mo.
Yes.
Yun lang.
Well, eventually pattern.
Thank you.
Natuwa ako sa evolutanin. At
thank you.
Vortex. So paano mo hahanapin yung vortex? So kailangan mo lang ng cardioid na aperture, di ba?
Yes. Actually, we've done this through simulation, and we see that there are a lot of discontinuity or singularities inside. Madami siya masyado.
But have you tried fabricating the cardioid?
The thing is, the DMD, you can actually program it to make a cardioid, and the difficulty is actually doing the interferometry and seeing what's in there inside the heart.
So you have to interfere.
If there's a vortex inside that. Yes, or you can do there are so many things, like you can do you can scan over with the triangle if you want, right? Triangle, you can see the discontinuities, but it is experimentally challenging because of that. Madami siya masyado. Madaming singularities sa puso.
Yes, okay. Okay, sige, something to think of.
Lalim ng hugot mo.
Okay, salamat.
Pwede bang can you use the structured light as Raman incident? Ano yan? Non-disclosure agreement.
Sensei Nori is here. So we were thinking, we have a research, one of my PhD students in Japan under Professor Nori, and this is one of the areas of our investigation. Yes.
Okay, good to know.
Does that answer your question?
Then we will do it.
Yung polygon slit, for example, as it's a closed surface, but it's quite irregular. And then nakita ko sa equation mo, there's a relation between the Z and L, which is yung lateral dimension ng slit. Geometric yung approach, but implicit ba ang wavelength dependence? Is there an implicit requirement that necessitates the lambda to be the same order of magnitude as L, or is there not?
Yes.
Okay.
Yes.
Okay.
Important siya. You cannot have this interference if the aperture is big. It's so big that you can't see the interferences.
Hence, napaka-importante ng linear polarization. Okay.
The thing also here is that the nice thing about here is that you can also use this technique for partially coherent beams. These are not, they don't have temporal coherence in the experiments in 1920s. They don't have a laser, but they were able to observe it. So I guess what they did is to manipulate the coherence of a broadband source. It's one of also of our research areas, how to manipulate coherences of say LED. And maybe if you plug it, I can plug it in an SPP in October. You would see one of our research where we it's a nice research for education in optics laboratory in undergraduate. It's just to control spatial coherence using pinhole, and it's a nice experiment.
Hindi kaya mas magandang, ewan ko, hindi kaya mas magandang idea na i-apply mo yung idea mo sa, hindi sa LED, kundi pulse laser? Kasi yung idea ng temporal and spatial coherence sa ultra-fast laser is very different as opposed to say helium neon. Pangit talaga. There's a paper by Val, si Percival, nag-measure sila ng temporal coherence ng femtosecond. And it's very limited. And this can be used to play around with the coherence length, coherence time of a ultra-fast laser pulse. It should be very interesting, very publishable.
Yung sa coherence length in pulse is what I'm actually talking about is the spatial coherence.
I see.
The spatial coherence, not the temporal coherence. Oo. Yung temporal coherence, di ba siya yung bandwidth ng LED? Di ba?
Pretty much.
1 over tau, or 1 over the bandwidth of the LED. But this is a spatial coherence, the relationship between 2 points in a space. That's what we are trying to control.
Pero hindi, kasi kunyari, to be able to achieve ultra-fast pulses, you'd have to have a wide bandwidth.
Yes.
So dapat, sa totoo lang, hindi siya truly monochromatic yung ultra-fast laser mo.
Yes.
So dapat mababa ang kanyang spatial coherence din.
Not necessarily. Mababa ang temporal coherence niya.
Alam natin yun.
Oo. Spatial coherence ay
hindi ba dapat?
Hindi
necessary.
Ako sigurado. Hindi ako sigurado.
Alright. Mali ako malamang. Alright. Thank you.
Thank you very much.
Interesting talk. Any other questions from the 22 participants left in this session? Otherwise,
Maiksing tanong na lang, Taning. Ano ginagawa ng geometric wave sa diffraction? Wala siyang kinalaman.
Meron siya kinalaman actually. Tinataas niya yung noise level. Kaya kami gumagamit
ng siya sa intensity, sa signal level lang siya may wala siyang
tapos nag-interfere din siya sa boundary. So yung pattern mo is the same pero tumataas lang siya.
Okay, so hindi siya nag-change yung structure ng diffraction pattern.
Hindi.
Noise level, signal level.
Okay. At least yung pagkakaintindi ko. Kasi pag ginagawa namin yung aperture, medyo mataas talaga yung signal level. Hindi namin makita yung structure.
Akala ko wala na akong time para i-present yung certificate of appreciation.
Well.
We do have time, so I'll do it anyway. Andali lang po before I let you go. All right. So, the certificate of appreciation is presented to Dr. Nathaniel P. Hermosa for delivering the lecture entitled Structured Light Optics for Engineering and Automation on 23rd July 2020 as part of Parallel Session 2.2 during the 40th PAASE anniversary and the 2020 Annual Meeting and Symposium, APAMS, Manila, Philippines, signed by Dr. Gisela P. Concepcion, PAASE President, and myself. Nat, thank you very much.
Thank you very much for the invitation.
Alam ko busy ka. Nat is the Deputy Director for Academic Affairs of NIP. And
until July 31st. So,
well, technically, every time I see an email about academic affairs, ikaw pa rin ang tinatanong at ikaw pa rin ang sumasagot. I have hands raised. Sorry, Nat, before I let you go.
Yes.
Ba yun?
Clapping yun.
Clapping, sorry.
Okay.
Pero may tanong pa ako kay Raf.
Oh, go.
Sige.
Ay,
Graph,
yun bang silver sa baba, how important is that for TERS?
Uh,
The lower level.
Actually, yung importance niya po is for the STM.
So, dapat laging may silver sa
Yes
ilalim.
po. So, not necessarily silver, but should be metal.
Any metal, right.
Yes po.
So, I was wondering if you could do the same on non-metal. Yung insulator siya. Like,
Yes po. So, if insulator, kailangan po is AFM. We can use an AFM.
Pero you can also measure the Raman as it scans the EFM.
Yes, should be, ma'am. But right now, I don't have such a thing.
Okay.
But classically po, yung
That's why
TERS is
usually.
AFM. So, yung mga AFM, yung mga TERS at room temperature and ambient conditions are usually in using AFM.
Kaya usually, it's the Raman, micro Ramans are coupled with AFM.
Yes po.
That's why. Okay, sige. Thank you. Thank you.
Thank you po.
Not pag-uusap pa tayo ha.
Mag-usap pa tayong apat.
Sige. Kahit hindi ngayon.
Okay, hindi ngayon.
So with that, I would like to thank all the participants, all those who had to wake, especially for those who are in the Philippines, who had to wake up a little earlier than usual, especially in these pandemic times, to join us, those who ask questions. Madami kayong naitulong sa amin. I didn't have to ask the questions that I wanted to ask na magmumukha lang akong tanga. And to our participants from abroad, sina Jack, Nori, I saw students from Osaka University a while ago, and our invited speakers, Raf, Mo, and Nath. Thank you very much. Okay.
Thank you.
Thank you.
With
Thank
that,
you again.
thank you. See you. I officially end this PAASE session. Thank you. See you guys. See you around. Stay safe. Bye-bye.
Yes, same to you.